In the previous video, we took a closer look at the most common types of engine dynamometers. Now we are going to look at how they can be used to generate torque curves. A torque curve can be generated by running the engine at a series of speed points. As an example, you could run the engine every 400 revolutions per minute from 800 RPM to 6,200 RPM. At each of these speed points, the speed and the torque values are recorded and the horsepower is calculated. Then, the points are plotted to create the torque and power curves. Again, just like different engines produce different torque and power curves, different dynamometers have specific uses, and they also generate unique torque and power curves. Therefore, different types of engine dynamometers are used for different purposes. When looking at these torque curves, the highest value on the curve is commonly referred to as the engine's torque rating. One other thing I want to point out is that at an engine speed of 5,252 revolutions per minute, the torque and horsepower are equal, meaning their curves intersect if you plot them on the same graph. This is based upon the equation for horsepower. Remember, to calculate horsepower, we divide by 5,252, so at the speed of 5,252 RPM, the 5,252 will cancel out, causing the torque to be equal to the horsepower. In these two images, we have two different torque and horsepower curves. On the left, we are looking at a Chevy Impala that runs on compressed natural gas, or CNG. Notice how the torque and horsepower curves intersect one another at 5,252 RPM. This engine has peak torque at higher speeds, somewhat close to the peak horsepower. In the picture on the right, we are looking at a 3.5-liter V6 EcoBoost engine. The top curve is power, and the bottom is torque. Here we have peak torque at lower speeds. If we were to overlay these two graphs, they would again intersect at 5,252 RPM. Like I mentioned before, both of these torque and horsepower curves were generated by running the engine at a series of speed intervals, and torque is recorded, and then the power is calculated. Diesel engines typically have slower speeds, and they have much lower power ratings. However, what matters for these engines is the torque, not the power. In a train or large truck, we want high amounts of torque in order to get the train or truck moving. In general, when you have low power, you have high torque, and when you have high power, you have lower torque. In engines that have peak torque at higher RPMs, like our Chevy Impala from before, the peak power is also greater. In engines having a very high peak torque, like motorcycles or Formula One engines, the peak horsepower can be up to 2 or more times the peak torque. Let's summarize everything we've just discussed. There is more to an engine than just the amount of power it has. The torque curve actually defines the engine. When you apply a load, an engine will respond on its torque curve. However, marketing techniques will always give the horsepower rating of an engine. Unfortunately, this doesn't give you the whole picture. It only gives you the amount of torque at one condition. The bad thing about strictly looking at a horsepower rating is that the engine is typically not ran where the peak horsepower is generated, because a lot of times that's around 6,000 RPM. A good consumer will always consider both the horsepower and the torque when comparing engines. This concludes our discussion of torque and power curves.